Now that we're more comfortable with limits, we're going to look at a better definition for continuity that's based in limits instead of our definition of being able to trace the function without picking up our pen. So this activity should lead us to our definition of continuity, our new definition. So we want to use the graph above, and I'm not going to keep showing it to you unless I need to, because you have a picture of it that you're looking at. So is the function defined at x equals -6? So g of -6 is undefined. So I don't have to figure out the value because there isn't one. So we're over here at -6. I kind of scan up and down. All I see is a hole. There's no function value, no height at which I know the function is for -6. What is the value of the limit as we approach from the left? Now they're saying x approaches a, so our a is -6. So the limit as I approach -6 from the left of g of x is 5. And I'm just looking at the graph. If you have trouble with that, you can ask me about it in class. Now we're going to check from the right. The limit as x approaches -6 from the right of g of x is also 5. So then what can I say about the limit? Well, the limit as x approaches -6 of g of x is 5. So we've got 5 because it's 5 from the left and it's 5 from the right. So now looking at the graph, is the function continuous at -6 using our informal definition of being able to trace it? So at -6, I'm tracing the graph. I have to pick up my pen over the hole, so therefore it is not continuous. All right, so I'm going to try to go a little bit faster through these next couple. So g of -3 is defined, and in fact it's 2. Now let's look at the limit as x approaches -3 from the left. It is 2. Let's look at the limit as x approaches -3 from the right. It is -4. So what does that mean the limit is? Again, the limit, we're just sort of focused on these two. The defined function doesn't matter for the limit, right? The first part. I do want to point that out. The defined part's going to matter for continuity, but not for if the limit exists. So in this case, the limit as x approaches -3 of g of x does not exist because they don't match from both sides. Looking at the graph, is this function continuous at -3? Definitely not. If I trace the function, I get to here, I got to pick up my pen and start over here. Function is not continuous. The key is going to be when we come to a continuous part, what happens with all of these values? Let's look at 0, the target value of 0. So g of 0 is in fact defined, it's -1. So if I look at 0, I go down to the graph, I have a point right there. Even though I haven't highlighted that point for you, right? When we have a graph, when we're drawing the line, we're drawing all infinite points all along that line. So there's a point right there at 0, and it is -1. Now let's check the limit as x approaches 0 from the left of g of x. That's going to be -1, because that's the height we're headed towards from the left. The limit as x approaches 0 from the right is the height that we're headed towards as we approach from the right. It's approaching a height of -1. Those two things together, right, these two guys, since they agree, that means the limit does exist. And it is in fact -1. Now let's look at the function at -1. If I trace it, I can go right through there, no problem. So the function is continuous at that target value. Let's move on for 2. G of 2 is undefined. The limit as x approaches 2 from the left of g of x. Sorry, my g's look like 6's, sort of. Is infinity. The limit as x approaches 2 from the right of g of x is -infinity. So therefore the limit as x approaches 2 of g of x does not exist. Now if we look at the graph at our target value of 2, as I approach 2 from the left, I definitely have to pick up my pencil and restart my tracing so the function is not continuous. Let's look at a target value of 6. So g of 6, that'll be fun. Do g's look like the 6's? Is defined and it's 1. The limit as x approaches 6 from the left of g of x is 4. The limit as x approaches 6 from the right of g of x is negative 2. So that implies that the limit as x approaches 6 of g of x does not exist because these disagree. Right, the 4 and the negative 2 from each side. If I look at the graph at 6, I'm tracing the graph. I do have to pick up my pencil to plot that and pick it up again and come back down here. So it is definitely not continuous. And our last target value of 8, g of 8 equals negative 4. The limit as x approaches 8 from the left of g of x equals negative 2. The limit as x approaches 8 from the right of g of x is equal to negative 2. Because those two limits agree, I know the limit as x approaches 8 of g of x equals negative 2. Let's look if it's continuous at 8. I'm tracing, I have to pick up my pen, come down here, define it, and then keep tracing. So no, it is not continuous. I had to pick up my pen. Alright, so this guy right here, oh, I don't have a yellow highlighter. This guy right here is the winner. So what can we conclude? What do we notice happens to make this thing continuous? The function is defined and its value is negative 1. The limit does exist and its value is negative 1. And that means the function is continuous at that x value. Okay, so now we're going to go back here and fill in kind of our 3 criteria. So this is for if we want to see if it's continuous at a target value, I like that green better, at a target value of a. Okay, so we're talking about just at any given x value a, what has to happen for it to be continuous. I'm going to actually give you the last one first. F of a has to equal the limit as x approaches a. And they have to equal L, which is whatever the number is. So in order for these two quantities to be equal, the f of a to equal the limit as x approaches a, they both have to actually exist. So that's really kind of the other 2 criteria. This step 3 is really all you would need to write to show that the function is continuous at a. You'd have to say that f of a is equal to the limit as x approaches a. When you make that statement, you're kind of saying the height of where it's headed, the limit, the height where it's headed or it's approaching, which is the limit, is equal to the height when it actually gets there, which is the f of a. And if those two things are equal, that means both of them have to exist. So that's what the first 2 parts say. The first part says, well, first of all, f of a must be defined. They're not really saying what it is, but it has to be defined. If it's undefined, there's no way that third statement can be true. If f of a is undefined in the first place, f of a cannot equal the limit as x approaches a. So that's sort of like your first criteria. The second criteria is the limit as x approaches a from the left of f of x. Let me say it this way. I like this better. The limit as x approaches a of f of x must exist. And remember, limits exist or do not exist. Function values in step 1 are defined or undefined. So the limit must exist. For the same reason, if the limit didn't exist, then step 3 couldn't be possible. You can't say f of a equals the limit as x approaches a if the limit does not even exist. So for the limit to exist, that means, keep in mind, that the limit as x approaches a from the left, there's a little left there, must equal the limit as x approaches a from the right of f of x by the existence theorem, and that has to be equal to some limit L, which of course is a real number. That's that limit existence theorem. So the 3 criteria really can be summed up nicely in one. If you make this statement, you're sort of implying the first 2 already. If the 2 things are equal, then that means f of a must have been defined and the limit must have existed. Okay? But that's our 3 criteria for a function to be continuous at a point. This is one, again, if you get an FRQ on the AP test and you have to explain reasoning from this unit, this is one of the more popular ones. And it doesn't come up often, but if it does, you're going to want to be able to explain yourself there. So we're going to work on that. So let's look at some examples where we have to explain ourselves. So here's a graph. It's not continuous at several x values. You can clearly tell that with I still go back to our layperson's kind of definition. If I trace it, I have to pick it up here. So there's a discontinuity at -8. Then at -6, sorry, is that 6? -4. I got to pick up my pen again. So it's not continuous there, and so on. There's a couple other places. I'm not going to go through them all right now. So they want us to talk about at each target value, use the 3-part definition of continuity to determine if the function is continuous or not. So at x equals 8, the first thing we need to check is 1, f, is this function f or g? This is function g. So sorry, I got to use g's. G of -8 is defined, and its value is 4. I don't really need that its value is 4 part. I can just say it's defined, but that 4 is going to be needed in the final step, so that's why we're figuring out what it is. If it's defined, you might as well go find out what it is. Again, not really needed for step 1. All you need to really say for step 1 is this. But it's helpful to have that value of 4 later. Part 2, you have to show the limit exists. So I can say the limit as x approaches -8 from the left of g of x equals -5, and the limit as x approaches -8 from the right of g of x equals -5. Therefore, or I'll use thus so it fits, the limit as x approaches -8, whoops. I'm not going over how I get these -5s. I'm hoping by this point we can do that. That looked like an infinity. You can ask me about it in class if you're not sure why I'm getting one of these limits or something from the graph. The limit as x approaches -8 of g of x exists. That's all you really need to say is this part up to here for part 2, but we are going to want to know what its value is. So we say the limit exists and its value is -5. So then criteria 3 for it to be continuous here is that g of -8, sorry, our target value, needs to be equal to the limit as x approaches -8, which it is not. So since they're not equal, I would say therefore, this time I have room, g of x is not continuous at x equals -8. That's the official definition. It's got to meet all 3 of those criteria. And why could I make this last statement and say they're not equal? Because along the way I found the values, right? I found that, let's see, I kind of want something a little lighter. I found that the defined value was 4, and the value of the limit was -5, and those are not the same. In other words, this function is headed towards, it's approaching a height of -5, But when you get to -8, the height's actually 4. So there's no way you have to pick up your pencil, right? As you're tracing, this part right here means you're tracing towards a height of -5. You're headed down towards -5. Then when you get to the x value of -8, you've got to pick up your pen, go define it at 4 because it's not where you were headed, and then go back down to -5 and leave from that height. So you can see how that's the picking up of the pen. It breaks that definition. Let's look at -6. All right, so criteria 1 or step 1 is that g of -6 must be defined. It is based on the graph. Its value, I'm going to need to know that for later, is -7. Step 2, the limit as x approaches -6 from the left of g of x equals -7, and the limit as x approaches -6 from the right of g of x equals -7. So the limit as x approaches -6 of g of x exists, and its value, I don't put an apostrophe there, its value is -7. So now I can see, before I go to the last step, that g of -6 is defined, and in fact it's at a height of -7. The limit exists, and its value is also a height of -7. So that means the limit is saying, as I approach, I'm heading towards a height of -7. When I get there, the height actually is -7. So then when I leave from -7, I'm not going to have to pick up my pen to execute that. So that's where that last thing comes in. Step 3 is going to say that g of -6 is equal to the limit as x approaches -6 of g of x. And you want to even kind of say what it is. That value is -7. I like to show that they're both equal to each other, and that value is -7. So therefore, I'm trying to do good with the explanations to set a good example. Therefore, g of x is continuous at x equals -6. Okay. The last one, g of -4 is defined, and its value is -5. The limit as x approaches -4 from the left of g of x is -5, and from the right, nice, is -2. Thus, the limit as x approaches -4 of g of x does not exist. Therefore, I don't even need to go any further. Therefore, g of x is not continuous at x equals -4. Why do I not need to go any further? Because once either the g of -4 is not defined, it's undefined, or the limit does not exist, there's no way step 3 is possible. They can't be equal if one of them is undefined or the other one doesn't exist, right? So you can just kind of stop at that point and just say it's not continuous, and therefore is only one word. Oh no, not move that guy. I'm going to try that again. There you go. That's better. Moving along. So we're going to look at some piecewise definitions of continuity. These are the ones where they try to trip you up. So let's take a look at this. Use a 3-part definition of continuity to determine if they're continuous or not. So step 1 at the given value. So our target value is -2. F of -2 is defined. How do we know that? You know what? I'm going to have to write a little smaller than this for this to fit. I'll do this. Okay. How do we know it's defined? Well, you have to look on here and choose when you're trying to do f of. Remember, it's not approaching. You got to find the spot right where it's equal to 2. And if it wasn't written like this, like if I just had, instead of this row, if I had this, I would just plug -2 into this part because it's less than or equal to. In this case, equals to gets its own kind of row here. So it's defined, and I can do direct substitution. I can plug -2 into the 3x plus 2. So it's defined, and it is 3 times -2 plus 2. What is that? -4. Okay. So step 1 complete. It is defined. Criteria, or step 2, is that the limit as x approaches 2 from the left. I should just do what it equals. Equals. So 2 from the left means I'm here. I'm on the x value is just less than -2. I should be saying -2, not 2. Sorry. This is -2 from the left. I'm at values just left of -2. That's what that represents, x less than -2. So I do direct substitution of -2. So I get -2, square root of -2 plus 6 equals -4. So that's the limit from the left. Now we have to do the limit from the right. So from the right, I'm choosing the function where x is slightly bigger than -2. And you do direct substitution. So on that guy, we're going to get e to the -2 plus cosine of -2 pi, which is, let's see, 1 over e squared. And then cosine of -2 pi gets me back at 0, so that's just 1. So that value is clearly not equal to -4. The limit from the left and the right do not agree. So therefore, we say the limit as x approaches -2 of f of x does not exist, and the function is not continuous. So the limit does not exist, therefore, one word this time, f of x is not continuous at x equals -2. Alright, it broke criteria 2, so we didn't have to go any further. Let's look at this guy. G of pi is defined, and its value, oh, I forgot to mention, our target value there is that pi. And its value is, we're going to do direct substitution on this guy because it's or equal to. So when it's equal to pi, I plug it in. I get e to the pi tangent of 3 pi over 4. Unit circle, e to the pi times -1 equals -e pi. You need unit circle help. Make an appointment. We'll go through it. I think I have a pretty good way to think of it, I believe, and so I can help you kind of figure that stuff out. If we have some class time when it starts to slow down here, which it will. I know we're going fast, but I'll do some unit circle review. So that's number 1. We get -e to the pi. Criteria 2, we got to do the limits now. So the limit as x approaches pi from the left of g of x equals, so now pi, left of pi is x less than pi, so we're doing direct substitution in this top guy. We're getting e to the pi cosine of pi. So that's going to be equal to e to the pi times -1, which is -e to the pi. We got to check the limit now as we approach pi from the right. So now we're back down on that bottom one. We do direct substitution, and hey, we're going to get the same thing here that we just did because it's direct substitution both for g of pi and the limit as x approaches pi from the right because it's kind of shared here in this criteria. So we don't have to really go through that one again. We already did it. It's negative e to the pi. So therefore that means the limit exists because they agree. So that's going to be the limit as x approaches pi of g of x is equal to negative e to the pi. Criteria 3, I should say, exists because we have to state that that's what they want. So therefore it exists, and its value is negative e to the pi. Criteria 3, we could say g of pi is equal to the limit as x approaches pi of g of x, and it's equal to, I can say the value that it's equal to show that I found it and I know what it is. They're both equal to that. Therefore, g of x is continuous at that target value. Now we're going to look at some questions that I love to ask. And they're going to give you some kind of unknowns in here, like an m and a k. And they'll say, like, what's the value of those have to be to make this function continuous? So just remember, if they ask you something like that, you just kind of have to go through and find m and k that makes all three of these guys true, all three criteria, then it will be continuous. It's not as hard as it sounds. This will sort of walk us through one. Actually, we're going to do two of these. What two limits must be equal in order for f of x to be continuous at x equals negative 1? So I look at negative 1, and this would represent the limit from the left. This would represent the limit from the right. And since it's also equal to at negative 1, we have to say then the limit as x approaches negative 1 from the left of f of x would have to be equal to the limit as x approaches negative 1 from the right of f of x. Now I do want to state that that's not the only thing to make it continuous. Okay? That's just the start of it. That would prove the limit exists. We'd still have to show that f of negative 1 is defined, which this equals will show, and then show that they're equal. But this is just sort of walking us through it. What two limits must equal in order to f of x be continuous at x equals 3? So at 3, it's going to be the limit as x approaches 3 from the left of f of x must be equal to the limit as x approaches 3 from the right of f of x. And of course, we still have to show that f of 3 also is equal to those guys to show that it's continuous. So now it's saying determine the values of m and k so that the function is continuous everywhere. So we want to show that when I plug negative 1 into here, getting the limit from the left will equal when I plug negative 1 in here. Those two things have to be equal. That will make it continuous at negative 1 because we have that equal to sign. Whoops, I want a different color. Now, to show that it's continuous at 3, because we have the equal sign, f of 3 is going to be just plugging it in there, right? So we want to show that when we plug 3 into that function and 3 into this function, that those are equal, and that's what would make it continuous everywhere. We're sort of skipping over like the criteria that f of negative 1 is defined because it's clearly defined. We'll talk about that in a second. So what you want to do to find these values is we're going to say that if I plug negative 1 into the top function, first we're going to do it at a target value of negative 1. So if I do direct substitution on the top function, that would represent the limit from the left needs to be equal to the limit from the right. So I plug negative 1 from the middle function because that's going to be from the right. And then I get m times negative 1 plus k. So I'm going to get 2 equals negative m plus k. Now that's got two variables, so I can't solve that equation for m or for k. Whenever you have two unknowns, you need two equations. So we're going to use another equation. We're going to now find the values that make it defined or make the function continuous at 3. So when I want to do 3 from the left, I'm going to do direct substitution with 3 into that middle function because that's on the left side of 3. The x is less than 3. So I go m times 3 plus k. I did my direct substitution. And then that's going to be equal to the limit as we approach from the right. Those are the x's bigger than 3. So I do direct substitution into the bottom function. It's just -2 because there's no x to plug into it. So if I simplify that, I get 3m plus k equals -2. There's my second equation. I can use these two equations to solve the system. So we're going to say -m plus k equals 2. I just flipped sides here. And the other equation will be 3m plus k equals -2. That's my system. I'm going to do elimination. So I'm going to multiply, let's see, I'm going to multiply the bottom function by a -1. So now I get -m plus k equals 2 and -3m minus k equals 2. Now I can add these. I will get my cancellation. That is 0, so I get -4m equals 4. So if I solve that equation, m equals -1. So there's my m. I can go plug that back into one of my original equations. I'll use this one right here. 3 times -1 plus k equals -2 plus k. Let me write that a little better. So I get -3 plus k equals -2. I add 3 and I get k equals 1. There's my m and my k that would make it continuous. We should kind of consider all the three criteria now if I were to plug those back in. But I would just say this. What is f of -1? That means since it's equal to -1 here, I do direct substitution. F of -1 is 2. And now with that new m and k, if I plug -1 in to the second function, I also get 2. So the limit from the left would be 2, the limit from the right would be 2, f of -1 would be 2, so the function would be continuous at 2 because the limit exists and is equal to f of -1, right? So that would be the same thing at 3, but let's do one more, last example. Consider that function to the right. What two limits must be equal in order for it to be continuous at -2? Well, we're going to do the same sort of thing. We would say like that the limit as x approaches -2 from the left of g of x has to be equal to the limit as x approaches -2 from the right of g of x. For it to be continuous at 3, the limit as x approaches 3 from the left of g of x has to be equal to the limit as x approaches 3 from the right of g of x. So then we can figure out the values for, what do we need here, k and m. So let's make our equations. Let's do the first one. To make it continuous at -2, I do direct substitution here to get the limit from the left. I do -2 direct substitution here to get the limit from the right. So we're going to get, we're plugging in a -2, so I get k times -2 squared plus m. It's going to be equal to 4 times -2 plus 1. So I get 4k plus m equals -7. And then if I do now the other value for 3, if I do the direct substitution in the middle here, that'll be 3 from the left. This will be 3 from the right. So I get 4 times 3 plus 1 has to be equal to k times 3 minus m. So I get 13 equals 3k minus m. So if I do my system by combining these two equations, because there's two variables, I need two equations. 4k plus m equals -7. 3k minus m equals 13. These are ready to add right away. I can add them. The m's cancel. 7k equals 6. K equals 6/7. And now I need to find m, so I can use any equation I want. I'll use this 3k minus m equals 13 and plug in my k. So I get 18 sevenths minus m equals 13. I'll change that into sevenths, would be what, 91 sevenths. 13 times 7, 10 times 70. 10 times 7, 70. 7 times 3 is 21, 91. So then I get negative m equals, I subtract my 18 sevenths. 91 minus the 18 is 73 sevenths. And then I deal with that negative. And there we go. Long video, but you only have one.